Hi Chem classes. Today we're going to talk about the differences between molecular formulas and empirical formulas and see how we can calculate empirical formulas from two different types of information. First, we're going to define molecular formula because molecular formula is the formula that you see. It's the actual formula for that particular compound, showing the actual ratio of elements in the compound. The empirical formula is the smallest whole number mole ratio of elements in a compound. So it may be the same as the molecular formula, or it may be a reduced version of the molecular formula. And it's important to note that when it comes to ionic compounds, all ionic compound formulas are empirical formulas, and there is no such thing as a molecular formula for an ionic compound because one, they don't exist as molecules, and two, because of their crystalline structure, we always write them in their lowest possible ratio, which would be empirical formulas. So let's take a look at what we mean by the differences between an empirical formula and a molecular formula. If we take an empirical formula like CH2O, I know it's an empirical formula because I cannot reduce the subscripts any further. Right? Those are the lowest whole numbers they could possibly be, C1H2O1. However, that same empirical formula can apply to a number of different molecules. All of these molecules in front of you now have the same empirical formula. They all have the same ratio of for every one carbon there are two hydrogens and one oxygen. But clearly they represent different actual molecules and have different molecular formulas. So here we have formaldehyde in its simplest form is CH2O. If we multiply all of the subscripts by 2, we end up with acetic acid, C2H4O2. If we multiply it by 3, we get lactic acid. If we multiply them all by 6, we get glucose. So all of these compounds have the same empirical formula, CH2O, when we reduce them all to their lowest whole number ratios, but they all have different molecular formulas. So let's see how we're going to find an empirical formula. When we think about finding an empirical formula, we have to take a step back and remember that a formula has subscripts, and those subscripts represent ratios. The ratios represent either atoms of an element or moles of an element. So if we're talking about a single molecule of something like acetic acid, we would be talking about individual atoms of each of the elements. But when we talk about a mole of acetic acid molecules, we are upping that ratio to mean moles of atoms. So 1 mole of acetic acid molecules contains 2 moles of carbon atoms, 4 moles of hydrogen atoms, and 2 moles of oxygen atoms. Our goal in the empirical formula is to find the lowest whole number ratio of those elements in the compound. So we want to find the smallest number of moles that represent the ratios in that compound. To do that, we're usually given one of two sets of information. We're either given percent composition, and percent composition is great because it's a percent. That means we can view it as if it were out of 100 grams. And so all we need to do is convert the percent to grams, and we're ready to go. And then we can also be given experimental mass data. And you don't have to do any conversion with that. You can just start out with the mass data. So let's take a look at an example of each of these two types of problems you would be given for empirical formula. So the first type, percent composition. Here we have lactic acid, and we know from an experimental analysis that it is 40% by mass of carbon, 6.71% by mass of hydrogen, and 53.3% by mass of oxygen. So we want to know what is the lowest whole number ratio of the carbon, hydrogen, and oxygen in lactic acid. What is its empirical formula? So again, everything we do has to do with comparing moles and finding mole ratios. So the first thing we're going to want to do with these values is convert them to moles. Now again, this is a percent composition. They all add up to 100%. So it's very simple. All I have to do is suppose I have a 100-gram sample of lactic acid. If I had a 100-gram sample of lactic acid, how many grams of it would be carbon? Well, 40, right? Because it's 40% carbon. So I can convert my 40 grams of carbon to moles of carbon. How much of it would be hydrogen? Again, 6.71 grams of the 100 grams would be hydrogen. Convert that to moles. And lastly, how about the oxygen? I'd have 53.3 grams of oxygen, and I'm going to convert that to moles. Now that I've calculated moles for each of my elements, I can actually use these mole values as subscripts in a formula. The only problem is these are not how we usually write a formula, right? We need to have whole numbers as our subscripts because we cannot have 0.331 atoms of carbon. We cannot have 0.657 atoms of hydrogen. So we have to make them into whole numbers. The easiest way to make these into whole numbers is to divide all of the subscripts here by the smallest one. So that's what we're going to do, the smallest one being 3.331. So if we divide all of the subscripts by 3.331, we get a ratio of 1 carbon to 1.998 hydrogens to 1 oxygen. Now that 1.998, that is real close to 2, right? Definitely close enough to 2. So I can see that I have a ratio of 1 to 2 to 1, which means I have an empirical formula for lactic acid, as we learned before, that is CH2O. Right? 1 carbon for every 2 hydrogens for every 1 oxygen. So that's the empirical formula based on percent composition. It works the exact same way if you're given experimental data, except you don't have to even think about if it has a percent and making it into a mass because you're already given a mass. So here we have an iron oxide analyzed in the lab, and it was found to contain 1.771 grams of iron and 0.6766 grams of oxygen. So here I have a ionic compound, right? I have iron oxide, ionic compound, but I don't know what the charge is on iron. And maybe even I don't know what the charge is on oxygen. Could have a different oxidation number as well. So let's find out the empirical formula based on this experimental data. We're going to go through the exact same procedure. So the first thing you're going to do is calculate the number of moles you have of each of the elements in this compound. So why don't you go ahead and do that? And you should have found that you got 0.0317 moles of iron and 0.04229 moles of oxygen. Okay, now again, the next step is to stick them into a formula. And boy, that does not look like a nice formula, right? So we want to make those into, again, whole numbers. The easiest way to do that is to divide by the smallest value that we have, right? The smallest number of moles we have. So in this case, the 0.03171 is our smallest value. When we divide that, of course, one of them is going to end up being a 1, in this case the iron, and the oxygen works out to be 1.334. So still not a nice small whole number. So what we're going to need to do, one last little step here, is we're going to need to multiply these values by small whole numbers until we get small whole numbers. All right, so the first thing I'm going to do is multiply them both by 2. If I multiply them both by 2, what would my subscript be? Right, so the iron would be 2, but the oxygen would be 2.668. Still not a small whole number. So let's go back to my original one. Now let's multiply it by 3. What would my subscripts be if I multiplied everything by 3? And now I get some nice subscripts. Now I get Fe3 and I get an O that is really close to 4, close enough to 4, right? So now I can say that my empirical formula for this compound is Fe3O4. Maybe it's not what you thought it was going to be, right? Based on what you know of oxygen and what you know of iron, but based on experimental data, this is the empirical formula for this compound. Okay, so let's look back at this slide again. First step, calculate the number of moles. Second step, use those moles as subscripts, even though they're messy. Then you're going to divide by the smallest number you have there, the smallest subscript you have. Lastly, if necessary, if you still don't end up with whole numbers, then you're going to multiply them all by 2 and see if that gives you a small whole number. You're going to multiply them all by 3 if you need to. If that gives you a small whole number, then you stop. Maybe you might have to multiply by 4. You might have to multiply by 5. Very, very rarely will you have to go beyond 3 or 4, but it's possible. Okay, so remember, multiply one at a time until you get a small whole number ratio for your final empirical formula. Now you know what's up next. It's time to practice, right? Problems with percent composition and problems with experimental mass data. As always, I'm here if you have any questions or problems, just let me know.